This is the Empower Podcast, released December 1st, 2019. Episode 469. An interview with Craig J. Bishop. Welcome to the Amp Hour. I'm Chris Gamble of Contextual Electronics.
And I'm Craig Bishop from Mango Dynamics.
Hey, Craig, how you doing?
Pretty good. Good, Chris.
It's almost the Thanksgiving holiday here in the U.S., so we're like having like a nice, easy pre-Thanksgiving, pre-gorging ourselves talk about electronics and everything else.
Yep, I'm fasting.
Yeah, you mentioned you have a couple Thanksgiving dinners to prepare for, so it's good. It's good.
Right. It's a problem when both families are in town. So.
Yep. So we got to hang out a little bit at SuperCon, and I asked you to come on the show. And I'd love to talk about the thing that you had in hand and then kind of work back to what you've worked on in the past. So what were you showing me at SuperCon?
All right. So at SuperCon, I had a large thing called a Games Lab wrapped around my neck, which when I received the official badge for SuperCon, I looked at it and I hadn't looked at it before, and I found out, hey, that's an FPGA badge. And I haven't worked with the Open Toolchain, so I don't know how fast I could get something running on that. But I brought this giant thing based on an FPGA. So why not? my friend Tom Shucker, who was there, just said, "Why don't you put that around your neck?"
Yeah, just add a lanyard. That's the badge
right,
now. Yeah.
Right. And he had a kit with zip ties and everything to kind of add a lanyard to it, and hung it around my neck, and it was
Bingo.
Heavy, but much easier.
2 days later, you got a sore neck and a lot of questions about it. So
exactly.
So now let's do a little disambiguation here. Is it Games Lab or is it a game slab or both?
So you could say it's both. Originally, I wanted it to be Game Slab because it's very slab-like.
It is. It's pretty beefy. Yeah.
It's over an inch thick, and it has a 10 amp hour battery on it. And, which at the time I thought it was gratuitous because the FPGA turned out to take a lot less power than I thought. But for SuperCon, that ended up working perfectly because it lasted all day.
Right. Yeah. Fewer charge cycles. And
yep.
So what is on this thing? This game slab? Slab of games.
So it's got a Xilinx Zynq FPGA ARM Cortex A9 combo. So the story behind that is for years I've been wanting to build a handheld console based on FPGA, and I've been looking at Zynq parts because they have a nice dual-core ARM built in. And on eBay, there's all kinds of chips you can buy on eBay. I heard someone at SuperCon call them. You can buy chips on tape. You can buy chips on reel, and on eBay you can buy chips on PCB. Which, like a lot of sellers on there, cut these chunks of PCB out of used electronics gear with an expensive chip on it.
Yeah. They don't even do the work for you of like removing it, and reballing it, and stuff like that.
Depends who you buy from. So a lot of time you'll see like literally in a eBay picture, you'll see a roughly cut out chunk of a PCB with like a Vertex 7 on there, which is, $10,000 chip. Yeah, and they don't want to risk it before they sell it to you. So they'll just sell it to you on the PCB.
They just like use a Sawzall or something, or how they
I don't know.
Some guy, that's crazy.
Some guy with a Dremel tool cutting these out.
Yeah. Oh man. Hopefully a mask too.
I found this seller, I think it was Jia Shungtong Chip Co. Something like that. That he
might
would
have
actually
to link for that later. Yeah, we'll see. Yeah. Unless you want to hide your source, we can always bleep that out too.
Yeah. He actually took them off the PCB and did the reballing for me. So he was selling them already reballed.
But he's upfront about it too. I think that's important. It's not like, oh, these are new parts. These are definitely reclaimed chips.
Yeah. Well, I think the term they said was refurbished. So.
Yeah, that fits the eBay aesthetic, right?
Right. Which I was still very skeptical, but if you look on eBay, so this is the XC7Z035, which is a really big Zynq part. And if you look on DigiKey or Avnet or Mouser, it's like a $1,200 chip. which of course their pricing is always high in onesies and twosies,
Sure,
and
sure, sure.
especially for
Yeah.
FPGAs, but still not
Right.
cheap. And
Yeah,
this
probably still a couple $100 in quantity kind of chips, right?
exactly.
These are
And
not
this,
these are not commercially viable chips, or not going in your consumer goods, rather.
yeah, no kidding.
Not in your
Maybe
games
a
lab.
snickerdoodle or something, but yeah,
Yeah,
exactly.
right. Right, yeah. So we
Um,
should say Ryan was on talking about similar parts a couple episodes ago, Ryan Cousins,
yep,
and that was the Snickerdoodle. But I think that was a much smaller part too. So less
yeah,
FPGA fabric. It still had the A9 cores, but less fabric around it.
yep. No, I had a lot of fun listening to that, and yeah. So this is a much bigger chip, which I only got because of this eBay guy. So probably a year ago, I found it on eBay, and I saw the price. I think it was 80 or $100 or something like that per chip, and I
Yeah,
impulse bought 5 of them because it's like I'll find something to do with these if they work.
yeah, definitely.
But I was still super skeptical about them actually working or not, because I read a lot about counterfeit chips, especially big chips like that, where you can take another chip and like Dremel off the markings, or
Yeah,
they
right. Just
they
re silk screen the bigger chip's
oh,
name or
apparently it
something like
happens
that.
all the time. So
Yeah.
Xilinx plastic LQFP and TQFP parts. Apparently, there's whole companies that sell kits for taking you Dremel off the top layer of plastic with the markings, and then there's actually this like epoxy that you put on top of it to mask that,
Oh my
and
god.
then you re-silk screen it.
I mean, that's a sign of just how much money there is in doing this counterfeiting, because that there's kits to do that kind of, like, that's crazy.
It's like hilarious to me, and I found the maybe we'll have to link to that. I think it's one of the national labs. I think has a PDF going through all the ways to identify possibly fake chips. And they have tons of Xilinx examples and other expensive
Yeah,
chip
yeah, yeah.
examples in there.
Actually,
And
yeah,
they're
that sounds
like,
like a great resource. Yeah.
oh, it's hilarious too, because you have to look for signs of sandblasting. It's like,
Wow. Wow.
so, yep. Anyway, so I got the 5 of these, and they arrived just fine. But in order to actually test them, you can't just power a few pins and throw a JTAG on there. It
That's
actually
right.
requires pretty much a whole board to be able to test it.
Yeah, because FPGAs always have, like, I think they've gotten better, but I remember they used to be like you have to like bring power supplies up at the same time, and you have to have, like, it's a significant amount of current too, even at
Yeah,
especially for the low, like the 0.9 volt rail,
right.
things that are going to the core.
Well, it turns out that the sequencing is not as catastrophic as it could be because I've messed that up a few times and it still lives.
Oh,
But
that's good. Yeah.
the power draw still is a big problem. And not just that, but the thing has tons and tons of power BGA balls on it. So,
Yeah.
to,
How big is this part as well? What is the BGA count?
so it's a 676 ball part. But it has
Okay.
a really easy pitch. It's a 1 millimeter pitch.
Yeah. Okay.
And so and before this, I had been working on a Zinc dev board, just playing around. So I had a bunch of software and a bunch of FPGA stuff ready to go. I just needed a board to try these out. And so
Yeah.
I decided to try to figure out if I could get a board for this part without spending $1,200 on a PCB as well.
Right.
And
So,
that's how it.
like, you're not a super high layer count kind of thing. Not super. I guess the pitch was good to start with.
Yeah. Well, if you look at things like, was it a Digilant Zybo, I think was the board I was using.
Yep. Yeah, that's one of their. Yep.
Yeah, I think it's an 8 or 10 layer board. And I didn't really feel like paying that much just for a board to figure out if these parts worked at all.
Right. Yeah.
But
Although eight, I
if,
mean, eight and 10 are getting cheaper, but not cheap, right? Not like,
yeah,
I'm
well, I
guessing you were
found,
trying to get to like JLC 6 layer type of thing, right?
well, that's exactly where I ended up actually.
Yeah.
Because JLC's 6 layer is the cheapest out there by far now for 6 layer, I found. Um, I think these
They're
were,
cheap. They're cheap on a lot of things.
yeah, yep.
I mean, quality too. Like, quality. But like, I think the pitch you need, and yeah, everything.
Yeah.
That sounds like it was a good start. So.
Well, the turns out the two key things were so it was a 210 by 100 millimeter board, I think, and it ended up being about $150 for 5, which is awesome. And the key things were the 6 layers and that they would do a stack up that matched the impedance for DDR3.
Yep.
And then
Yep.
also their via diameter was small enough because the DDR3 chip is a 0.8 millimeter pitch.
Oh, I see. Okay, so even though the FPGA was okay, the memory was more
Yeah,
challenging. Yeah.
yeah. And so I should eventually publish my blog post about that, but figuring out that the impedance and the right stack up for the DDR3 routing on 6 layers was interesting because it turns out that if you use the top and bottom layer on the JLC PCB 1.2 millimeters thick stack up, then you get a pretty nice microstrip that gets you somewhere close to 50 ohms, which is still above the 40 ohms for DDR3 that it's in the datasheet, but it's close enough and it's just one chip, so it should work. And then to use an internal layer, it it changes the impedance and then it also changes the propagation delay. So this is where I learned some fun tricks in KiCad, or I guess fun tricks combining KiCad and Excel, because it turns out, so KiCad has length matching, but when you're routing a high-speed interface like this, you actually want delay matching.
Right. Yep.
And when you have traces on different layers, internal and external, they have different delays per distance traveled. And
right. So if you need to hop between layers, you're saying it's difficult.
Yeah, exactly. So I had this
challenging. Yeah. Yeah.
Yeah, exactly. So I had this giant Excel sheet with length on layer 1, length on layer 3, length on back layer, and it would multiply out by the delay on each layer, and then it would calculate the skew for every net, and then it would show me whether those skews are within the spec or not. And then I also had to, so these FPGA parts are so big, they actually have a delay on chip too before the signal gets to the BGA. And so you also have to throw that delay in there.
Or how do you is that just like a spec thing?
Yeah, it's kind of annoying to get. You have to go into the vendor tool and have it spit it out for you. But it gives you picoseconds delay. It doesn't give you like a length because the length is not what matters.
Right. Yeah, I guess even the length, you're really trying to get to the delay as well, right?
Right, right. And I think KiCad eventually will have delay based matching, but right now it just has length based.
Yep. Okay.
So
well, so you got through that. It sounds like. I mean, like it's. So then, what was the boot up process like? I mean, how did you validate what was going on?
So the first thing is after got a first board back. So the board has DDR3, the Zynq, USB transceiver, and let's see, it has some power management stuff. Like there's a STM32 on there for managing the power sequencing and battery. And then there's a TI battery management part. And once I got it back, the first thing to check out was the power supplies, which I like using Rust now for all my embedded firmware development.
And Chris White just had an aneurysm. He likes really poking fun at him, but yeah, okay. We'd love to hear about this though. Yeah,
yeah. Which we can talk about that more later. But it's been a great experience so far.
Yeah.
And so I loaded minimal code to bring up the switching regulators and try to get the sequencing right. And that's where I mentioned if you get the sequencing wrong, it doesn't seem like things blow up.
Yeah. Spoken from experience, it sounds like.
Right. And then once the power supplies are up, the first thing I do is throw a JTAG debugger on there to see if it even sees the FPGA. And more key, see what part it says it is.
Right. Oh, yeah, because that's what you were trying to get to in the first place, right? To validate this is actually what you'd bought.
And so
just real quick on this. So you were running Rust, and like you said, we'll talk about this more later, but you were running Rust on the A9 on board, is that right?
So Rust is running 3 places on here. It's running on the STM32 that's running all the power management and the battery management. That thing's an L0, so it's always on. And then it's also running in kernel modules in Linux on the A9 because when you put custom hardware in the FPGA, you have to write drivers and stuff for it.
Yep.
And writing drivers in Rust is still not fun, but it was an experiment.
Sure.
And
it sounds like this whole thing is a playground for you, right?
Yeah, basically. And then the games are also written in Rust in user space.
Oh, cool. Okay.
So everywhere possible.
Great. I mean, it's your party, man. You get to play with how you want.
Right.
I didn't quite get
Exactly.
that. So when you said STM, you said an ST part doing all that stuff. So you meant it was actually like a supervisor micro on there that then
Yeah.
is it built into like a broader power management chip, or is it separate from the power management chips, and then the STM32 is actually like talking to those chips over I2C?
So I looked at some integrated power management, but I actually really wanted, since this is just an experimental thing, I really wanted to try Rust. So I wanted an ARM part, and then I wanted to monitor all the power rails separately. So I have a current sense on all the power rails and voltage sense and current and
Oh,
voltage sense
nice.
on the battery,
Yeah.
because I had no idea how much power the Zinc chip was going to take for different workloads. So I
Yeah.
really wanted to have everything on there to be able to monitor that.
That's great. I mean, and the L0 chips are SIP power, and they're yeah. So what, you just have like an external instrumentation amps around like a sense resistor or what?
Yeah, so there's I think 5 sense resistors on there, and each of them has a fixed gain amp on it going into the ADC. And then there's I think one of the rails has a voltage divider to get it into the range of the ADC.
Yeah, that makes
That
sense.
and then it's one of my favorite parts. It's a TI. I should look up the name of that part. BQ24250, I think.
Yeah, I was gonna say it's definitely something BQ2400,000 family, right? Because that's all
Yeah,
the charging chips. Yeah.
and it's a 2 amp charger if the
Uh huh.
system's not running, but it switches the system load between the battery and the adapter automatically.
Uh huh.
That chip is amazing.
Yeah, those things are great. I mean, they just kind of they don't just work, but like and they have like control registers, and a lot of them have control registers
Right.
now too, right? So you can do some configuration stuff in there. But
Yep.
um,
And
that's
I was
cool.
actually really afraid of that chip at first because I hadn't done battery management stuff before. So I actually built a separate board first to prototype just that, and ended up being completely unnecessary because it worked out of the box. So yeah, I highly recommend those chips. Not cheap
Yeah,
though.
yeah. It's no, they're not. They're like $4 or $5, right?
Exactly.
Yeah.
Yep.
Well, again, this is a playground for you, so that's when if you take the Game Slab, to product, I think a lot of things will change.
My supply
I'm
chain
guessing
needs
this
some
is not
work.
going to make it to. I'm not going to make. I'm going to say it's not going to make it to the market. What are your plans there?
Yeah, not as is. So
Yeah.
it's yeah, the even eBay pricing the $80-$100 FPGA is still a little bit bomb busting.
Yeah. Yeah,
So
that definitely is. Okay, so you
yep.
got this thing up and running. That's great. And then the JTAG was to so you had to get the JTAG chain up and running to even talk to the A9. Is that right? Or is it
So
to talk
there's
to the
a
rest of the FPGA?
yeah. So the Zinc parts actually are different than other FPGAs that they don't necessarily go out to a bitstream flash first. They actually boot up the dual Cortex A9, and that ARM part of the chip actually controls bringing up the FPGA side. So you get JTAG access to the ARM side first and boot up the ARM processors and make sure those work. And then from there, you can do whatever you want to boot up the FPGA fabric. And
Huh.
so in my case, I worked out getting the debug UART to go through the STM32 over USB with creating a firmware for that. And then after I had debug out, then I worked on putting U-boot into the boot flash, so that way the Zinc would boot up U-boot bootloader, and I had to port that. And then once you have U-boot, you can actually think about booting something like Linux. And
Huh.
that part actually ended up being okay because I had already tried all that on the Zinc dev board, and it was just a bunch of fiddling with configs and stuff to get it ported over to the new board.
Yeah. So
And
the U boot you had to. So the U boot was that in Logic? Any of those steps were in Logic, or were those all software still?
so that's all software. And
Okay.
then the logic piece is so the Zinc has no graphics output or anything like that built in. It doesn't have a built in GPU or anything. So,
No, you got to build that, silly. Come on.
yeah,
What are you doing
exactly.
here?
So, the idea with the Games Lab is that every game brings its own hardware. So,
Yeah. Which is
And
similar to the how the SuperCon badge was too, right? That same idea of
yeah, exactly.
portability. It's a cool idea for sure.
Yeah, that was really cool. And you could do it a custom game, brings its own graphics hardware exactly suited for its needs. Or I thought with the Games Lab, which I started working on, if you want to do like a Game Boy emulator, instead of emulating the Game Boy in software, I just plop a Game Boy CPU and graphics hardware into the FPGA fabric, and it kind of
Yeah,
becomes a Game
that's
Boy instead of
that
emulating
is
one.
super fun.
Yeah.
Yeah.
So I actually
And
started
what does
working
that
on
look
a
like? What yeah, what does that look like? I mean, what is the Game Boy hardware? I have no idea what it looks like.
Oh, so I have a series of blog posts on that, at least work in progress, and it's a funky Z80 that custom developed by the I think it was Sharp that made it for them,
Uh-huh.
and the funkiness is that it has an extra instruction set with a prefix that's all the bit manipulation instructions, which were used for a lot of graphics effects and stuff.
Mm.
And it's a single and it's in order and it's not pipeline. So it's a really easy processor to try to implement in the FPGA. And it only runs at like 4 megahertz, if that.
Yeah, it's amazing what they did on those. I mean, the things that I spent so much time on in my youth. It's like,
Oh,
the
yeah.
pretty
All the,
simple processors, they're so cost optimized, all that stuff, but like they did so much with them.
oh, yeah. Well, and all the secret sauces in the graphics hardware that goes with it, the sprites and the tile maps and all that.
Mm. Yeah. And so
So,
this is the blog post starting Slab Boy, is that right?
yeah, that's the one. And that was
Yeah.
kind of so when I'm doing this FPGA stuff, especially on the experiment like Games Lab, I really, really don't like to write Verilog. So I'm trying to switch entirely over to an alternate HDL. And my favorite one is called Spinal HDL, which is
So
kind
if
of
people
an.
couldn't tell here, Craig is a software minded person who likes to take the barrier. Like for me, I'm like, whatever is the most documented, most easiest, whatever the most people have done, so I can look something up on Stack Overflow. It sounds like you're like, nah, I'll just figure it out. So why? Why?
Well, it's kind of like I do enough stuff for work and now consulting that is very well documented and has to work in production and stuff. So when it comes to this side project, I want to use everything experimental and see what happens. And
Okay,
a lot
I
of
mean,
times I actually
it's
find stuff that I end up using in actual work.
I mean, it's really it's very noble and awesome, and like experimental that you're doing all this stuff. I can't imagine myself doing. That's really that's I can't empathize with you, Craig. I'm sorry about that, but it's awesome.
Well, I
You're a
do
little
end up.
crazy, but it's like the right kind of crazy. You know what I mean? Like it's like that's super cool.
It's
So
stay up till 3 a.m. because this compiler
yeah,
doesn't support the one specific flag you need. Crazy. So,
yeah, totally. I've definitely done that.
which I don't know.
So okay, so what is spine? So you said spinal HDL, is that right?
Yeah, so huge shout out to Charles Popon. I don't know how to pronounce that, but he's a guy, I think in Switzerland or Austria, somewhere over there, that created Spinal HDL, which started out as a fork of Chisel, which is the Berkeley hardware description language. And they're both based on Scala, which is a programming language running on the Java VM. And I know that's a long chain, but basically it means that it's a strongly typed hardware description language built in a full programming language. So Verilog is kind of its own thing, built just for hardware description, and it's kind of a rather limited programming language with a lot of capability to describe hardware. And it's also
Right.
loosely typed. So Verilog, like the canonical example is, oh, I'm going to assign this 32-bit bus to one wire, and Verilog says, okay, no problem. Versus a language like Chisel or Spinal HDL, you'll get an error when you try to synthesize that, telling you, hey, you're trying to connect two buses that don't fit together. You probably don't mean to do
Oh.
that. Tell me what you actually want.
Okay. And so is that I don't actually know what strongly or weakly typed means. What does that mean?
So weakly typed is kind of a programming language concept that's been uh, applied to hardware description languages. I don't know how well it fits, but basically, for example, if I have a integer that I can't just turn an integer into a floating point number without some kind of conversion in the middle, So like C would be a loosely typed language. For example, I can cast anything to a pointer, and I can cast that pointer to whatever I want, do whatever
Yeah.
I want.
Yeah. Right. You got to kind of keep the structures in your head almost, or well, I guess you have to state them somewhere. But at the
Yeah.
end of the day, you're manipulating data. A char is a byte is a
Yep.
is a
Exactly.
uint8, whatever, right? And it can be converted. You're saying that is not the case in loosely typed.
Yeah. So loosely typed languages, that is the case where a char is a byte or is a float. Sure, whatever goes. And Verilog is like that. So, and this can it can be good because it can actually help development speed and let you do things in C that you can't do otherwise. But when it comes
Yeah,
to designing,
it's bowling without the bumpers on, though, right?
yeah, exactly. And
lot of
designing
gutter balls.
FPGA hardware is hard enough already. So adding that complexity on top of it, where if you mess something up because you're tracking all these wires in your head and you connect two buses together and you forgot to put a converter or a mux or something in the middle, and it just silently does it anyway, and then you're stuck trying to figure out what it did. It's kind of
Usually there's a warning buried in the 550 other warnings that I had. So
right. Well, and 500 of those are warnings you just ignore every time anyway. So
right.
yeah.
So what about like a VHDL? Isn't that more? I mean, that's more explicit at least. I don't know if that fits the strongly typed thing, but VHDL is very complainy. I know that from my past.
Yeah. So I'm pretty sure when I say this that VHDL is strongly typed. Someone will probably correct me, but it is way more verbose.
Totally.
And
Yeah, you got to basically like state it in three places and make sure everything matches, and it'll give you lots of it'll talk your ear off.
right. So someone at Berkeley a while ago, I don't know exactly, went Goldilocks on this, and I want strongly typed, but I don't want too verbose. So they went and created their own HDL called Chisel, which was based on the language Scala, which is strongly typed, but it's also really flexible. So you can basically create your own language within an existing language. And they called it a domain specific language, and they created Chisel for describing hardware. And the coolest thing is, kind of like the other popular new HDLs, is it spits out Verilog or VHDL. So whatever you write in it, it just spits out Verilog that you feed into all the tools you already use.
Got it. So this is like the MyHDL, LightX, MyGen, all of these other tools that are out there that are starting in Python and going to something else.
Exactly.
So it's like a layer above a layer.
Yeah, I think Verilog is becoming like the assembly language of FPGAs and stuff. So that way we don't directly deal with it most of the time, but if you want to know it for debugging and stuff. So
That's interesting. That's an interesting idea, actually, because is there a layer below Verilog? I mean, there is, right? Because all the
like
when
the
they're
netlist
synthesizing.
or
Yeah, right.
Yeah, and that seems like even further below, and maybe it's analogous to when you compile code. It takes your code and it creates a abstract syntax tree and then goes to machine code. So there's a few layers there too. So maybe it's analogous.
Yeah,
I don't know.
Real FPGA programmers program the registers themselves, and they push their own bit streams that they've hand coded.
Right. I write my values for my lookup tables by hand.
Exactly. Yeah. Someone out there is nodding their head right now, and they shouldn't be, but they probably are.
Yeah. Well, real FPGA guys calculate the timing delay on every wire themselves. So
yeah. Right.
Yeah.
Well, it's interesting. So, like, how big of a project? Like, is this pretty niche still? I mean, like, what's the?
So, Spinal HDL is gaining acceptance. Like, people at SuperCon mentioned it, which is great. So it's not some super
it's in the
niche
wind.
thing. And it has big followers, like the guy who does Zip CPU. I forgot his name, but awesome guy. Writes all kinds of tutorials online and has all kinds of stuff about formal verification. But he's also a big Spinal HDL fan. And I think the reason a lot of people like it, and the reason I came to it, is that a lot of stuff that you don't want to write but you need. For example, an AXI bus. So AXI is the bus standard used a lot in FPGAs, at least by Xilinx. And it's a complicated bus protocol. It comes from ARM, and it has a lot of stuff you have to get right. And if you're doing a Verilog, you have to do all this complicated logic. And then they tell you, oh, use our bus verification model, which kind of probes your thing in a test bench to make sure it's working correctly and does all these checks. So it's a huge pain. Versus in Spinal HDL, they have the concept they stole from programming land of a standard library, and you just import the AXI bus and you import an AXI slave factory and you tell it, hey, I want to register on this bus at this address, and I want this line of that register to go to this LED or something. And so it takes all that verbosity and it uses this already verified standard library to allow you to create peripherals very quickly.
Yeah, that's great. Wow.
So I don't like writing.
That library idea is interesting. I mean, like, does Verilog has like modules, but I guess do they not have libraries? I don't actually know how that would work.
So there's a lot of stuff out there for Verilog. A lot of it's for money, or people develop IP, and then a lot of times you can find code for AXI slaves or masters, but it's not modular enough to include wherever you want. Versus the power.
It's not just like call it and you're done.
Yeah. Well, and I think that's kind of the big power of using a full programming language to create the harder description language, is that I can use everything in that programming language, like the for loops and if statements and everything, to kind of be a meta layer. So I'm writing a program that generates hardware. So, for example, the AXI bus, instead of just describing one specific AXI bus slave, I'm writing a subroutine that takes in parameters like what you want and then generates the AXI slave based on that. So probably the best example is the same guy who created Spinal HDL is also behind Vex RISC-V, which is an amazing implementation of RISC-V. And when you get the project, you can turn on and off all these different parameters. Do you want a memory management unit? Do you want floating point? Do you want vector? And it generates a whole different CPU depending on what parameters you put in.
It's like a pull-down menu for CPU generation.
Yeah, basically. It's what do you want? And it'll give it to you.
Yeah. Order. You have it your way.
Right. And people have been doing this. Like with Verilog, people create all these Python scripts or Tickle scripts, which
I say Tickle, yeah.
And to generate Verilog based on inputs and stuff. But then now you're adding this whole other layer of complexity versus something like Spinal HDL. It's all one language, so it's really easy to shove it all together.
Yeah, and I do like that idea of like the benefit of libraries too is like, sometimes there are bugs in libraries. That is not an uncommon thing. But if you have libraries, you have people just looking at it over and over and over again. You just get reuse to the point of, you get more eyeballs on it. You can get more proof in the field kind of thing. So that sounds kind of great.
Yep. Or like a really good example is in the Spinal HDL standard library. There's a clock domain crossing standard library primitives, which is really hard to get right otherwise in FPGA. There's kind of subtle problems. So that's just a standard library piece you can plop down, and now you cross clock domains safely.
Yeah. My favorite was always going from like why do they have 33 megahertz, and then I'm like trying to go to 50. It's like that division does not look good. Right. And there's much weirder than that too. But it was just that one always stuck out to me of like just weird divisors and stuff like that.
Right. Well, and like we said before, it'd just be one error, or not even error, a warning message in a sea of 500 other ones. And
that's right. But it just don't work,
Yep, exactly. So,
yeah. So okay. So all this, you're using this to generate the thing, and then so what is inside of one of the examples that you're? So I guess you're doing a Game Boy type of thing, but like, what else are you creating in there? You're also creating other types of peripheral hardware, or what?
Yeah, so the one I had running at SuperCon was a frame buffer for the LCD, which ended up just being pretty simple peripheral because it just has to kind of count out data from memory onto the screen. And then it also had some 2D graphics acceleration. So instead of the CPU having to copy all this memory around to draw graphics to the screen, I created some hardware that you feed it a command list. So draw this graphic at this position on the screen and with this color being transparent, and it's a list of these in memory, and then the hardware goes through that list in memory and fetches that memory and draws it to the destination, like the frame buffer for the screen. And because it's in hardware, I can do things like operate on 8 pixels at a time, so it becomes a lot more faster than the CPU.
Huh. That's great. Yeah. And is this the kind of stuff that would be normally in like a accelerator engine? Like how did you know to go and structure it like this? Did you kind of borrow from something else or just come up with it on your own?
Well, the architecture, I wanted to experiment, so I kind of came up with that on my own, but it's inspired by like how 2D acceleration worked, or at least used to work for a standard PC. Like when you draw a window on the screen, usually your OS tells the graphics hardware, hey, draw this rectangle from this place in memory to this place in memory to put the window on the screen.
Uh-huh.
And the hardware takes care of that because it does a really fast, they called a bit blit from back in the days when you're moving bits around.
Hmm. Yeah, I'm still real shaky on how all the graphic stuff works. Like I talked about it with Sprite when they're, I think it was Sprite and maybe Sylvain when they were on the show during SuperCon. But like I'm just still how did you go and pick that kind of stuff up? Like did you used to do stuff with the software hardware side of things for PC hardware or what?
So back when I was a kid, I learned to program when I was a kid because I wanted to make video games.
Okay.
So my dad brought home the Visual Basic 6 step-by-step book, and the rest is history. But I always wanted to make video games, and I would play them, and I was more fascinated by how they worked than the actual game. And at some point,
that's a healthy that's a good way to change your from making income to spending income kind of thing. Game designers make income, game players don't make as much income.
Well, eventually it turns out that going in the games industry is maybe not the best idea.
Oh, it's tough. Yeah, it's a tough place. Yeah.
So but I always wanted to make games, at least up until a certain point. And so eventually, if you're a real game programmer, you learn C and you write your games in C. So learn C, which not a very friendly language learning as a kid, because like the loose typing we talked about. And so learn how to do that with this. I forget what book it was, but it kind of did tile maps and sprites and kind of the similar stuff that you'd have on the old style game systems. But eventually, I think this was middle high school, and I had been playing with microcontrollers and stuff like that, because back then, Microchip and Atmel and all these companies did free samples, which is amazing. Yeah. You just send them a request and you get chips in the mail from wherever.
You're a high schooler, right? Yeah, you want to get something done.
Yeah. So I wanted to, I was like, okay, I know C now, and I've written C on some microcontrollers. How do I create my own game hardware now? Because I want to actually do what the game console developers do and actually write games on consoles. And at the time, that was really hard because Nintendo doesn't want you creating games for their hardware. So
yeah, right.
If you want to do that, well, create your own hardware, I guess. Or I later found.
So this is the project where you made the Game Sphere. Is that right? Is that what we're going towards here?
Yeah. So that was before that. I made like a microcontroller based black and white TV game console where it had, I think, a PIC microcontroller generating the NTSC black and white video signal.
Yeah.
And
that's great.
That was cool. But I really wanted to create.
What was that using to do that?
So if I remember, it was a PIC 18F452, which I think was the biggest I could get in a 40-pin DIP and at the time. So it was on a breadboard, and it had very carefully timed assembly loops to spit out the NTSC signal. And because black and white didn't have a color burst, you could do it with just a, I think, 3-bit DAC made of resistors.
Oh, nice. Wow. And so this is not what became the Game Sphere, though? This is something prior to that?
Yeah, so prior to the Game Sphere, I was a kid playing around with NTSC video signals, which not fun, but it was the TV I had at that point. Yeah. And generating...
Here's what you got,
Yeah. Well, and creating HDMI out of a microcontroller, which existed at the time, but that was complicated, not something I could have done. But so at the Game Sphere, I decided, I don't like NTSC, so I'm going to try to create VGA and then convert VGA to NTSC. The Game Sphere was actually built with another ARM microcontroller. It was a free sample from Atmel, and that was a AT91R4000 or something like that. And I was actually inspired. This guy, Andre Lamoth, which anyone who wanted to be a game developer as a kid will recognize the name because he wrote all of the books about game development.
Okay.
And he wrote a book called The Black Art of Video Game Console Design. And it was amazing as a kid because it's basically like a half of a bachelor's in electrical engineering in one half of the book. And then the other half of the book is how to design game consoles based on that.
Wow. That's awesome.
It's still an amazing book.
Is it still in print or no?
I think so.
Okay. Yeah, we'll put it in the show notes for sure. That sounds like a kind of book where you hand it to a niece or nephew, and you're like, hey kid, go learn yourself some electronics, and then come back in 5 years and they're like you.
That book was a goldmine, especially written by a guy who he has a huge history of writing game development books and wrote games and ran a game publication company and stuff. And you get this book from him, and as a kid, you're just blown away because he shows you, hey, you can actually make a game console.
Yeah, why stop at software? Make the whole damn thing.
Exactly. And some of his videos online, I had seen he was using this particular Atmel chip because it's one of the last Atmel ARM parts that has a fully external bus on it. So it had 256K of internal SRAM, and then it had an external bus that you could hang whatever you wanted on, kind of like the old retro CPUs.
So it's still a microcontroller because it has internal memory, but you can get at it.
Well, and it had peripherals on it, but it had this giant external bus, which was amazing.
Yeah, that's great.
And I
had probably a signal integrity nightmare, but it's probably not going that fast. How fast is it going?
So I ran that part at 100 megahertz, which was another awesome thing.
Yeah, that's pretty fast.
Yeah, and then let's see, there was a flash chip off of it, and then another part which I guess started the habit of using expensive parts because it was a Cypress dual port SRAM for the frame buffer.
Okay. Yeah.
And that's, I think, like a $50 part or something like that.
Yeah. Wow.
But it was a free sample. So why not? That part.
Well, the why not is if you blow it up and you can't get a second sample, but I guess,
Well, they send you
if
3.
You told them Yeah, there you go. There you go. Yeah.
Yeah, just keep requesting free samples over and over and over.
Right. Did you come up with different company names, and are you in their database multiple times?
I think I used the high school email address that no one ever used.
Yeah, nice.
It worked. It had edu, so that worked.
Yeah, that helps. Well, this is great. And you said people are still calling you about this thing too.
Yeah, so I get emails and messages online all the time from what I assume are university students doing final projects, asking me if I can send them schematics or I can send them the design files. And
do you just send them the picture of the wire wrap board that you made? Because that should be enough to. That's enough to scare me off. That's for sure.
Oh yeah, you mentioned signal integrity. Well, 17-year-old me did not know about signal integrity, so this thing is a rat's nest of wires.
I mean, sometimes it's better not to know, honestly.
Exactly. It mostly worked.
Yeah, exactly.
And
this is a great post.
I'm pretty sure a lot of these are final projects, and that I politely try to tell them, well, I actually don't really have schematics for it, so even if I did, I'm not sure I'd give them to you then either. But
Right. This is kind of your job to do the hard work.
Right. So It's funny to still get that.
It's nice to know that the project lives on.
Yeah, somewhat. And but hey, that project did have a really important effect on my life because it directly led to my, well, I guess you would say second job, but first big boy job, which was. It turned out that my neighbor up the street, and this was right when I was about to go to university, the neighbor up the street was starting a semiconductor packaging company, as you do. And he had just gotten...
everybody has that neighbor, really.
Yeah, exactly. I didn't expect it in our neighborhood, but it was cool. And he came down and, because my dad and him were sharing a beer, and he's like, oh, what's this? And wanted to see the game sphere, and we started talking, and he told me he just got $120 million in funding to go start the semiconductor packaging company because, fabs are expensive. It requires a lot of money.
Yes, they are. Yeah.
And he's like, I have a graphics problem, and I think you could solve this. Okay.
And that's just, I mean, Craig, I think people are listening are convinced that you are a very bright person, and it sounds like as a high schooler you were a very bright person. But it takes a special brand of crazy to then talk to a 17-year-old high schooler and say, "Hello, I'd like you to fix my problem, please, with my $120 million."
Oh, I owe a lot to this man, Tim Olson.
Yeah,
Brilliant
yeah,
guy, and you're
yeah,
exactly right. He has the right kind of crazy, and he found
yeah,
a kid crazy enough to say, "Okay,"
yeah. Right, right.
which,
That's
looking
awesome.
back, is absolutely nuts. I had no idea what I was doing or getting into or anything.
That is fantastic. So what were you getting into? Tell us.
So, Deca Technologies, that he was starting, they're building a factory in the Philippines, and then with hundreds of $1 million of fab equipment. And they were building what at the time or still used, I think, in a lot of stuff called wafer level chip scale packaging, which I learned all this at the time is brand new to me. I'm like, oh, it doesn't have pins. It's not a dip or an LQFP or what is this? It's not even
Right.
a
Where do you hook?
QFN.
How do you hook this thing into a breadboard?
Exactly. But it turns out in modern phones like iPhones and Samsungs and that wire bonds. So, like, if you think back to probably university or something, they teach you about chip packaging and they show you these tiny little gold wires going from the chip over to the pins. And they have a big problem that they're really thick. Like, their Z height is really big. They take up lots of
Yeah,
room. And
they're
also,
inductors.
exactly, exactly. And so those went away a long time ago, by the way. So anyone who still thinks in wire bonds, you are kind of behind, except for
Well, I mean,
specialized
dip
things.
packages are they're still there, right? They're
Yeah.
still a thing, but
Well, and they came back
they
for a
don't want
while
to be doing it.
for chip stacking, and because through silicon vias are really expensive, so you just do a wire bond
Yeah.
instead.
Oh, really? You go like around the edge, kind of
Yeah,
just
you
do like
kind
a
of
little chip sandwich.
exactly. They do these weird things where they take a big chip and then stack a smaller chip so the die pads are both are exposed. And then if you get really fancy, they do this thing where they stack them back and forth and they actually wire bond in the little cavity between the two chips.
Yeah, that's
It gets
bananas.
crazy.
So what year is this too? Like what year is this roughly?
2010.
Okay.
So this is
Wow.
after iPhone came out, and every company who's at all involved in the cell phone business is trying to get thin. And so they came up with a new type of package called a wafer level chip scale package, or WLCSP. And this gets rid of all the wire bonds.
Yeah, that's the one that people are going to recognize. Like, oh, that really tiny one that's terrible
Oh,
for
exactly.
soldering.
Or if you
Yeah,
remember on
yeah.
the Raspberry Pi when it was light sensitive because the one chip was
Yep.
just like a die on the board, that's a
Yep.
wafer
Yep.
level CSP.
It's a huge photo inductor, or photo
Exactly.
diode. Yeah,
Oh,
yeah,
the whole substrate of my chip is a photodiode.
that's right. Although it
But
was like xenon bulbs, wasn't it? Like certain type of bulbs that really did it.
yeah, I forget exactly.
It was
But
like a higher energy, higher
yeah.
photon input, but still, like, yeah, it's
But
ground bounds with photons, kind of thing.
right. But that was the whole idea of the package though, is you get rid of everything. So they make these things, they literally take the wafer from the fab, like TSMC or TI or wherever it's coming from, and they don't cut it up. And so you take a whole wafer and then you go to a packaging fab and there's no wire bonders or anything like that. There's a bunch more equipment that looks kind of like semiconductor fab equipment, very close. And you put a couple more layers of metal on it. So you create like polymer insulator, and you create little vias, and you create a couple layers of copper routing. And the whole job of the traces on this is to take signals from the chip out to solder balls, and the solder balls are put right on top of the wafer. So at the end, you
Right.
get a wafer covered in solder balls, and then finally you cut it up into little chips.
Yeah, that's crazy too. I mean, like, what are the relative thicknesses? So like, you have a silicon wafer
Probably
that's less than a millimeter. I don't even know anymore. What is
coming
like a
in, it's probably 500 microns or thicker. And usually they grind them down, so the final chips are probably a few hundred microns. It depends.
and then you're saying that then they stack some other layers like a mechanical layer. This is effectively like a mechanical layer, right? Above that.
You basically have the incoming wafer from the fab, and we put a squishy layer of polymer on it, and then the copper routing. And the whole job of the squishy polymer is to kind of translate between the mechanical properties of silicon, which is very stiff and brittle, and the mechanical properties of your circuit board. And the solder balls also help with this because solder is a little bit squishy, like it can be, it's a little bit ductile.
Mm-hmm.
So when
It
your
used to be
phone,
more ductile, but now the no lead thing, you know.
yeah. And
Yeah.
so when your phone heats up and cools down repeatedly as you use it, or take it to cold weather, hot weather, the PCB inside has a pretty relatively high coefficient of thermal expansion, so it expands and contracts quite a bit, at least compared to silicon. And so if you
Mhm.
directly connect silicon to that, then you'll crack your silicon as your PCB expands apart.
Yeah, yeah.
So the goal is to kind of buffer between those two. And that's what the package does. But now you have competing constraints that I want the thinnest possible package, but I still want to absorb that stress.
Hmm.
So that was kind of the start. But where I came in for the graphics problem was an extension to that technology, which is hard to explain without talking about that, because what the goal was, we want to take the wafer level CSP and make the package bigger without making the silicon bigger, because silicon's really expensive. And the problem with the wafer level CSP is I can only fit so many solder balls in the size of a chip.
Right. So let's do some I guess some simple math here, right? So if it's like a
Sure.
2 millimeter by 2 millimeter square,
Yep.
and you have like 1 millimeter pitch,
Oh, that'd be
right?
huge for this. Like, let's say
It'd be
like
huge for that, right?
0.5.
Okay, so like what, 0.5 millimeter pitch? Then you still only could fit 4 across.
Right.
Is that right?
Yep.
Yeah, 4 across in either direction. So that'd be like a 16-pin PGA, right?
Yep.
And so now you're saying that they want to shrink it down to a 1 millimeter by 1 millimeter chip, and so you'd only be able to fit an equivalent of 4 solder balls on there,
Right.
and that would be not good.
Exactly. Well, and it's kind of the competing interests, because you have the chip makers that if they can shrink the silicon, that's amazing economically. But on the other end, their customers are designing these PCBs, and if you shrink the pitch on me or shrink the solder balls, you made my life way harder and more expensive.
That's right. Right, and not to mention spins and everything else, right?
Exactly. And I have to do high density interconnect on the PCB, and I have to, buy really tiny vias, like laser drilled vias and all kinds of stuff.
Yeah, right.
It adds up fast.
Yeah, especially if you're churning out millions of, like, this is high volume
Oh, yeah.
phones and
Billions.
commercial stuff anyways, right?
Yep. So these guys at Infineon, I think in 2007, 2008, they came up with this technology called EWLB. And there's all kinds of acronym soup in this industry, but basically the idea was that when I get the wafer, instead of just putting my layers right on top of it, then I'm going to cut it up, and then I'm going to use a pick and place machine, just like for PCBs, and take all these die and put them in some double-sided sticky tape on a steel plate. And I'm going to leave a little bit of a gap in between each chip. And then after I place them all on this double-sided sticky tape, I do an epoxy mold across all of them, and it creates what looks like a plastic wafer with a bunch of chips stuck in it, and the top surface is flat.
Yeah.
And then once I have this plastic wafer, then I put it into my wafer level CSP process, and I build polymer and copper layers and put solder balls on it and cut it up. So I end up with a bunch of chips that have silicon die kind of embedded in it, and a bunch of plastic around that kind of artificially makes the chip bigger without using more silicon.
Oh, so the plastic wafer is a structural piece, you're saying?
Yeah. So these chips, it's kind of, we'll have to link into a picture that it literally looks like a wafer, and then it has a bunch of rectangles in the wafer that are the silicon.
And then how does the how are the pads exposed on the silicon, on the chip itself?
So there's a couple.
If the whole
thing
gets gooped,
Yeah, there's a couple of ways. So on the EWLB kind, the die pads on the chip are actually directly exposed. So they stick those into the sticky tape. So then when you mold over the thing and pull off the sticky tape, all those connections are exposed, and you build on top of that.
Mm-hmm.
And then there's another method, which the company I worked at did, Deca Technologies. They did where you, on the wafer, before you cut it up, you build some little copper posts on all the connections, and then you stick those in, and you mold on top of that, and then you grind and expose the copper.
Got it.
So there's all kinds of ways to do it.
Right. So it's basically like, it's almost, it's like you're saying, it's basically making like a PCB process now, where you're now adding, so like the copper posts you're talking about are effectively like vias.
Yep.
I mean, there's always vias. There's vias in silicon too.
Yep.
Obviously, there's, these are just things that happen, but Wow, this is really nuts. And so again, so you're adding this like plastic passivation layer to add structural strength and to make it a bigger thing. But then
Yes.
the idea is that you're basically spreading out the pins to match a larger pitch part.
So you can't really spread out the pitch of the die, but the idea is that if I make the area bigger where I can put solder balls, because now I have
Uh-huh.
this flat plastic extension of my chip, so I can fit more solder balls on my package. And then the other benefit is now my chip is contained in plastic, which is kind of squishy and buffers me from stress.
Yep, yep.
And then also, which is a really powerful thing, is I can put two different chips next to each other. And then when I create this plastic wafer, I have two chips next to each other, and I can actually route copper wires, or traces in this case, between those two chips and create two chips in one package.
Ah, okay. So this starts to get into the surface, it was SOMs or what are they called?
Yeah, like
SIPs or
system in
SOMs or
package. Yeah, SIP.
yeah.
So
Okay. So I had always assumed that those were still doing bonding, but like you said earlier, nobody really does wire bonding anymore.
it has its niche uses, but it's for mobile like phones and stuff. It's way too thick.
Got it. Okay, so it's a height issue, and it's just not. Yeah, they're not gonna mess around with that.
Well, and electrically, it's not fun either when you're doing
Sure,
like high
sure,
speed
sure. Yeah, you
memory and
slow everything down. Yeah,
exactly. And
yeah.
so the big problem though is and this is a problem the industry struggled with and it kind of held back the adoption of this technology, is that when you pick and place these chips onto the sticky tape, the pick and place doesn't place everything exactly where you want it to go.
Ah, okay. Now we're getting back to the graphics problem.
Yeah, and so you end up with like, oh, that chip was supposed to go here, but it's 30 microns to the left and 10 microns up from where it was supposed to go. And
Come on, guys. Jeez, 30 whole microns.
well, you laugh, but a die pad is typically 50 to 70 microns.
Oh no, I know. I mean, yeah, I used to work in very small kind of things, but
Yep.
like, it's all relative scales, right? I mean, we're
Right.
going from things that we can see with our eye down to things that are very,
Yep.
very, 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 very small. So
Exactly.
I know it matters.
And so you could fix this problem, which one way the industry experimented with, and some companies do this, is that you buy really expensive pick and place machines that go down to
Oh, so they're super accurate.
Yeah, exactly, like 2 micron.
Yeah.
But the other problem is those go really slow. So you have to buy lots of them if you want them to keep up with your factory.
Yep.
And so Tim, the guy who hired me, didn't want to do that. And so he decided that I would rather buy really fast machines and buy a few of them, because if you have to buy lots of machines, capital cost adds up really quickly, and they have to make up that over all the chips. So your chip cost
and
goes
he only
up.
had 120 million, and that could actually take it. You need a factory and workers and everything else.
Oh
and
yeah.
Yeah, like picking places can't be 100 million of that. It's too much.
Oh yeah. We actually calculated out once that I think to do approximately one wafer a minute, we would have had to spend 32 to 50 million dollars on just pick and place machines.
Oh my god.
It was insane.
Yeah.
So his idea instead was, well, what if we just measure where they went and then create a new pattern that matches where they went?
Wow.
So the idea was we take the plastic wafer after we mold it, and then we put it under a metrology system, like an automated microscope. And for every chip, it measures its X, Y, and rotation away from where it was meant to go. And then the idea was we feed these offsets into this black box of software that then spits out a new pattern that matches those rotations and offsets.
Okay, and just as a reminder, you're doing this as a high schooler, or near to college person.
I didn't do so well in college, mostly because I was spending all my time working on this.
Never let my schooling get in the way of my education, huh?
yeah. I mean, it was a lot of fun though. I learned so much stuff from it, and it really jump-started everything in my career. So
wow. So okay, so you do have to do these transforms, but it's like, does the metrology equipment spit out some kind of like outlines, or what was the output that then you used to actually do the mathematical translations?
it would give you the X X offset from where it was designed to be, the Y offset, and the rotation. And then the software would take those, and first it would figure out, am I even in a valid range? Because if it went too far, we had no hope. So we had to check that first.
And that's like you just throw that one away then if it's too bad.
Yep, there'd be a yield loss. And then the goal was not to have too many of those. So, and then after that, we had one method where if you're just putting one chip in a package, all you have to kind of do is take some of the wiring patterns and offset and rotate them to match. So you take the vias and you move them over so they hit the die pad on center again instead of being off floating somewhere else. And then you take all the little traces and rotate and move them to match as well. And that works for one chip. But then as soon as you have two chips, or for some other reasons, really big chips, then things get complicated because I can't rotate and offset one pattern to match two chips.
Right.
And so that's when we had to create a system for actually auto routing between these two chips on the fly.
He said the magic word.
Yeah.
What was that on like Pee-wee's Playhouse or something? Like your alarm goes off, or you get like gack dumped on you, or something like that. You know?
Yeah. No, I'm the crazy auto routing guy. I was at KeyCon.
Yeah.
The crazy guy who likes auto routers.
Yeah. I definitely want to talk about that in a few minutes here too.
So the whole idea was that now for every chip, we would auto route between the two chips because they'd have some random combination of offsets between them. And we needed to create traces between them. And then once every chip gets its unique pattern, there might be like 5,000 of these on a single plastic wafer. Then we send them off to the lithography tool, which for those of you listening, like you're thinking, wow, how'd you create a unique mask for everything? Well, the answer is we didn't use a mask. So
that's right.
It was a maskless lithography. So we just feed in a new pattern for every wafer. And so every 30 seconds, we generate 5,000 new package lithography patterns and send them out to this lithography equipment that would draw them on the wafer.
Yeah, and this is kind of crazy too. So it's at the lithography level. What is like the feature sizes we're talking about here too?
Sure. So at the time, it was, I think the lithography had a 1 micron resolution, but you couldn't make lines that small. I think the lines are like 15, and then 10 micron line in space was solid. I think we proved we could go down to 5 micron line in space if we were really careful.
Yeah. So this is interesting too, because this is at the chip level, but it's actually like, from my mind, it's like you are literally doing like PCBs. You're doing very, very tiny etching of PCBs.
Oh, absolutely.
Yeah.
Yep.
And it's it is lithography, but it's basically you guys are pulling together the layout process and the Gerber generation, quote unquote, of course, right? The Gerber generation in this case is the data files that then get pushed to the lithography, which is then pulling in the fab process.
Yep. Yep.
And this is really trippy.
It really is like a PCB design process because so fab design for front end chips, you have so many constraints like orthogonal only metal lines and let alone all the device constraints. And for package design, it really looks like a PCB design. In fact, I always laugh because Cadence sells this CAD tool that you use for it called System and Package Designer. And it's actually Cadence Allegro, which is the PCB tool, just rebadged with some extra features for package design.
Oh, yeah.
So it really is PCB design, just with smaller sizes.
And then you have to use Cadence Allegro, so that's...
Yeah. Well,
it's its own thing.
Yeah. Well, and actually, high-density PCBs, they actually use the very, very similar build-up process, too, in the fab to manufacture them. So,
okay. All right.
Yep. They both use electroplated copper. So it's just kind of all
merging, right?
Yeah, it's really blurring together now. Yep.
How accessible is so I decide I want to go and put two chips onto a package in a SIP type of thing. How much money do I have to knock on the door with, and how are there even firms that will do this from a on demand kind of design thing?
There are actually. So I used to know the names of some of them, but you can find them. It's mega dollars. So, and then if you're going to do the kind of technology I'm talking about, generally the first question is, are you Apple or are you Samsung? So,
yeah, right. People who actually need it, right? I mean, that makes sense.
Yep.
But I can imagine that, at some point in the future, as 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 feature sizes, everything just keeps shrinking,
Yep.
there are going to be non-Apples, not probably, Chris
Yep.
Gambles, but like non-Apples that are at the point where they need to do something like this, where they're like, yeah, we're just buying the die and making our own SIPs
Well,
because it's
I
better.
I absolutely think that's the future. I think we're going to get to the point where we stop putting solder balls on these things because it just becomes the whole system. Because I get rid of this whole intermediate step of going from a die to a package to a PCB board, and I just go from a die to a system in plastic, basically.
Yeah.
So, and that's already started to happen. Like the Apple with the Apple Watch, that module in there, they're basically leading the charge in this direction that they want to get rid of everything that's not super relevant to actually connecting these die together.
Yeah.
And
Yeah.
it's kind of crazy because if you think about it, when you, or I guess I think about it, that when you have two packages sitting on a circuit board next to each other and you have connections between them, you're going from a 14 nanometer transistor to a 70 micron die pad to a 1,000 time bigger, like 15 micron trace on a package to a 0.5 millimeter pitch BGA to a 8 mil trace on a PCB, and then going back down that stack on the other side.
That's right. Yeah.
So
That's a great point.
You're probably going through a million, divide and multiply by a million in terms of size on each side.
Yeah, and it's like, you could say, well, why not just put all the silicon together then? But then you start to lose the interoperability in this, and obviously that is happening, right? So,
Yep.
SoCs keep getting crazier and crazier.
Yep.
But if you need flexibility, if you need to be able to swap things out, the access to chip design is still even more remote, like just the more mega dollar.
There's a few problems too. So first is designing an SoC is really expensive. So even if you're using a lot of pre-built blocks, it's still probably a $50-100 million endeavor if you're doing anything size, decent enough size. And then also as your chip gets bigger, your yield goes down. So you kind of have competing economics there.
Right. Yeah, that's a great point. Yeah, because you're saying, so, and this kind of plays back to the chip size shrinking. That often happens during like a cost down phase in the chip designer, right? Where they want to use less space, they can drop the price, they can get more efficiencies. And then, like you're saying, higher yield because, variabilities when Chris, the former etch engineer, messes something up and everything around the edge of the 300 millimeter wafer is no good anymore, well, you still get 70% of the wafer to be good, but the larger the atomic piece on that die on that wafer, the fewer or the more likely that larger piece might be messed up.
Exactly. Yep.
Yeah.
And so that's why at the cutting edge, big companies are exploring things they call like split die architecture. So they take what was formerly a monolithic SoC, so one piece of silicon, and they split it into a few pieces. And they do it for yield. They also do it for, let's say, on your SoC, you only have so much design resources. So one year I spend my design team working on improving the processor. And then maybe next year I work on improving the sensors or the radio or something like that. If I have only one die, I kind of have to synchronize those based on my tape out of the whole die. But if I'm using two different die, I can have those design teams operate very independently, as long as they agree on the interface in the middle.
Yeah, that's right. And they do not use lithography that is on demand. It is large max sets that are very, very expensive.
Right. Yeah, prototyping costs
and getting more expensive.
Yeah, exactly. Yep.
Yeah. I have been reading about, I think it was an EE Times article about chiplets and stuff like that. Is that kind of the same realm of what we're talking about here?
Yeah. So one of the big guys in that space, Dr. Subu, he talks at a lot of the IEEE conferences. He talks about chiplets, and he's famous for showing where one whole wafer is actually one device. So it's one chip that's the size of a wafer.
Wait, what the hell is that?
So what he does is
like a 12-inch wafer, like a 300 millimeter wafer, or what?
I think it was a 12-inch wafer, and they manufactured all these chiplets. So all these die that were memories, CPUs, other specialized things, and they bond them all into this giant wafer. And the giant wafer is basically an interconnect between all these chiplets. And
so they're doing interconnect now on silicon instead of like what you're talking about in plastic.
Yeah, but so his idea is, I'm going to prove that we can make a giant system out of all these chiplets. But then it turns out, most applications cannot afford that if you're not like some military radar or something. So then that's where other technologies, like instead of using silicon,
Right.
I can use cheap plastic and connect these together.
Got it. I got it. So that's like basically them saying we could do it and this is the best way to do it, but you're saying, yeah, but it's cheaper if you do it the other
Yeah,
way.
turns out a lot of things out there that people want to build care about cost. So,
Yep. Yeah. Yeah. Same here. I'm a cheapskate, man. Yeah.
right.
Um, so what does this look like then? Okay, so let's get back to the actual. So you're doing an auto route now
Yep.
between. Let's just say we're gonna have our example here is gonna be. Can we say a processor and a DRAM? Is that
Sure.
realistic, or what does it? What does it look like between the two? Does it?
Or like,
I,
I think one of the ones we did was a microcontroller and a BLE chip. And it was right when BLE was
perfect.
exploding, and they didn't have time to integrate a BLE. So, like, I have
Yeah.
my die from the microcontroller and the BLE
Okay.
chip. Can you put them next to each other and connect them?
Okay. So that's great. So now, so maybe going between them is like a memory bus and some enable signals and power and stuff like that.
Yep.
But does that mean you only have one layer to go? So now, is this the effective like a one layer circuit board between two chips?
So, you could do more than one layer, but you
But do
typically
you?
wanted to avoid that if you could, because the more
Okay.
layers you add, the more chance you have for a yield loss.
All right. So now, so we're gonna keep it on one layer.
Yep.
So now we're looking at subject ABC123. We've taken photos of both the die. The die for the micro is fine. The Bluetooth chip is a little bit rotated and off a little bit. So now you go and well, you tell me. So what happens next? So you're doing the auto route piece then, or what?
So first, what happens is we called it at the time, and there's like an IEEE publication about this. If you really want to know the details, adaptive alignment. So we would take the pattern for each die, which would kind of have like the connections to the die pads and the routes away from those, and we would take those and rotate and offset those separately to match each die, and then there would be these little stubs left kind of between the chips. And so those we actually created a full custom auto router to generate routes between those that obey all the design rules.
Okay.
And so the input to the router would be, hey, avoid this stuff, maintain spacing to this stuff, route within this area, and obey these design rules, and route between to basically connect the dots between these two die.
Is this so? This is the paper that you linked to me, or no?
Yes, that talks about it.
Okay.
And
So there's a picture that has green and blue VGA pads. It looks like.
yep,
And then a bunch of like small dots that the traces are going to, and I'll link the picture at least.
yep,
So that is the auto routing, and it really does. It looks like a PCB, but
yep,
it's actually underneath the BGAs that's happening.
right. And so if you see the little red lines, those are the generated auto routes between the two die.
Mm. Oh, I see. So okay, so and I'm gonna try and paint a picture here for people that aren't able to go look at this thing. The die itself, it has stuff around the periphery of the die, right? So if you look at a 2 millimeter by 2 millimeter chip, all of the landing pads are on the edge, right? That's what the
Yep,
small dots are. Okay, and so then you're saying that there are pre-made routes that are happening to break out those landing pads on the die out to the BGA,
right.
but not all of those are the connections that are necessary to get between the two die that are also being broken out.
Yep.
Okay.
And part of the reason too is that so the blue and the green or teal part are actually rotated and offset to match those two die, but we don't
Ah.
we don't auto route in the middle of those, because when you're doing a package design and changing it on the fly, and you talk to a product engineer at your customer, they freak out on you because you're changing their design. Don't do that.
That's right. Yeah. Right.
So
Right.
what we had to
Wow.
tell them is, well, we're only changing this little bit, this like 100
Yeah.
micron struts of your trace. So you don't have
Yep.
to worry, it'll be fine.
Right. Nobody's having to simulate anything, folks. It's cool.
Exactly.
Yeah.
So,
Yeah.
and
Just a little nudge.
we were crazy when we started this. People, thought, really? No way I'll let that in my product. But
Yeah.
it turns out that if you're only rerouting 100 microns or so, that it really doesn't have much impact on signal integrity or anything.
Yeah. It's good to know.
So,
So let's talk about auto routers then. So this is the other thing. So you gave a talk at KaiCon, like you said,
Yep.
and it wasn't necessarily about PCB, like the PCB stuff, like KiCad or similar. But
Mhm.
but you're doing this stuff on a daily basis, and it's a lot better. That's what I remember. Is like this is it's not your grandpa's auto router. That's kind of the idea.
Yeah. Well, no, I yeah. So I'm kind of embarrassed about that talk a little bit because I got up there to say, hey, autorouters are good because it lets us focus on the parts that humans are good at: part selection, system design, fiddling with different trade-offs, and not think about the layout part. And PCBs are so cheap now that why would I really want to get to a prototype fast and try it, because I could spend forever trying to simulate or figure something out when I could buy a $2 JLC PCB and just try it. So really
Yeah.
the biggest barrier to me is just getting the layout done and in my hands.
Right. But the problem is that the tools that are maybe available to people at KaiCon or similar were not the ones that you're writing.
Yeah, well, and so at KeyCon, I demoed how to use free routing, which, don't get me wrong, free routing is an amazing project for being completely open source. And
Yeah, yeah, yep.
but it's still not using quite state of the art routing methods, auto routing methods. And that's where I think I mentioned that if you want to use a state of the art topological auto router, the best one I know of right now is called Topo R. And they actually do have free version, I think, and it's not that expensive in the scheme of things. Um,
Hmm.
but auto routers and other tools are kind of being deprecated, or everything's lending toward interactive design instead of
Hmm.
auto routing. When I feel like we should go the other way, where we want to do more like generative design. So I give all my constraints to the tool and it generates what my design should look, and I tweak it here and there, give it new constraints. But so I can iterate really quickly and focus on what I'm good at, the computer's not good at.
And what is interactive designs like a push and shove kind of thing?
Yeah, or like some of them have, you can route 12 traces at once and it'll kind of dodge
Oh
around
yeah, drag it
obstacles
along.
for you, or
Hmm.
if you set up your DDR bus, then it'll route that for you. But even then, I kind of get some of my software side is showing, because I'm like, DDR3 is a standard spec. Why are you having me set up all these constraints over again? I'm like copying
Right.
and
Yeah.
pasting from this PDF. Why isn't there just some library of constraints I can dump in?
Because you haven't made the tool yet, Craig. I mean, come on, like just get on this, and then we can just use it. Like that's. I think that's. Honestly, I think this is an interesting split too, where oftentimes as a hardware person using a piece of open source software like KiCad, I'm just like, I can't fix, and to be fair, many of the developers that are on KiCad are hardware people that are doing software and stuff like that. But
Right? You almost
it
have to
feels
be.
like it's, yeah, right, of course. But like it is the skills. It's so much the skills gap. Whereas you are not cursed with that skills gap. You have the bridge.
I
So
am crazy. So.
well, I wasn't gonna say that, but
Yep.
But yeah, I think some of that is right. And so, what is it going to take to bring some of these methods to projects like KiCad or similar?
Yeah. So I have this ultra secret take over the world plan, where that we build a not an auto router, because we got to do, and that's another thing that kind of peeves me about existing auto routers is, okay, it's not all about the routes, because also I want you to take care of the copper planes for me and figure out my power islands, and
Yeah,
I
right, right.
I care about the placement of some parts, but most parts I really don't. Like
Yeah,
where this pull-up resistor goes, it really doesn't matter. So whatever is necessary for the routing, just move it around for me, please.
yeah. Give it like so again. It's like developing constraints and then just kind of do whatever you want to say. And that's the generative design, like you were saying.
Yeah, exactly. And then beyond that, and at first I thought these were separate, but it turns out that I'm I'm gonna have to like take 10 years and off of doing any productive make money work and just go do this, because
Okay,
it's like
all right.
the so remember the Skittle talk at KeyCon where we talked
Yep,
about,
that was Dave Vandenbout. Yep, yep.
yeah, which is amazing talk because it was exactly what I was thinking about at the time, and he just did it and it works really well. And it's where instead of drawing schematics with pictures and boxes and little wires, that use a language in this case Python, to describe your circuit. And kind of like using a harder description language on SOCs or FPGAs, you can do a lot of stuff really efficiently, and you can kind of create like meta programs that generate your circuit for you. Like one of the examples I love is if you're designing a 555 Blinky, instead of having to go to the PDF and go into the formulas and put in your parameters to calculate your capacitor and resistor, you can just call a function like 555 A stable with my frequency I want and maybe one of the resistor values I want, and it'll create that chunk of circuit for me.
Yeah, it's great.
I really, really love that idea because so many schematics, like especially when you're working on big parts like FPGAs or DDR or stuff like that, it's a giant box with a bunch of little wire stubs with a bunch of labels. And then on another page, there's another giant box with a bunch of little stubs and a bunch of little labels. So the graphics aren't buying me anything. In fact, it makes it hard because now I have to go search where these little labels match up.
Yeah, and then if you label the inner between the things wrong, you can get things. So like if I have data 1 on the little box and it says, data line 1, and then I label it data line 0 and then somewhere else.
Classic.
It's hooked to like, or even if I label them data line 1, and then it's just labeled wrong somewhere else, just
exactly.
You can totally get things wrong, and there's no checking there.
Right.
But again, I think this is a skills gap thing, right? It's like if I was writing software, I'd write software, like.
Well,
and
I think these two should go together hand in hand, because another reason that people don't use autorouters today is because they're okay. They produce decent results, but it takes me just as long to set it up to do that as it does to actually use it.
Yeah.
And so
right.
The idea is one day, hopefully soon, we'll have this description language for circuit boards and circuit board components where that description can include things like layout constraints. So when I plop down my DDR3 part on my circuit board, it actually comes with these constraint definitions of how the autorouter should handle it.
Mm-hmm.
And then my life is good because I can use whatever part I want, and I don't have to spend days reading these 1,000-page PDFs on how to use it.
Right.
So, or even in the simple case, I think it's ridiculous. Like when we, like for example, even using a 555 timer, you put it in your schematic, and then you go in the PDF, scroll to the application example page, and you just copy that to your schematic editor.
Yeah. Well, I mean, we talked a little bit about this at KaiCon too. So, I mean, like, people can always go and listen to that episode. Honestly, that whole week was a blur. So I don't remember exactly what we talked about there.
Yep.
But I remember talking to you at some point about the idea of like having like with generative design too, like throwing it to a server, or maybe this is in your talk too, like throwing it to a server and having lots of iteration on it.
Yeah.
Too.
Well,
so what would that look like? Or is that kind of like what you do now for your work, or what?
Yeah. So for the very specialized autorouters for the packaging stuff, we run that on a cluster of servers because it has to be very fast. So it's 5,000 packages every 30 seconds or so. So it has to autoroute a lot of things.
Yeah, that's pretty fun.
And when you look at even the top of the end commercial autorouters out there, they're running on your laptop or on your workstation. And a lot of them aren't even really threaded very well. So you end up only exploring whatever your laptop CPU is capable of. And for a complicated circuit board, the routing problem can get complex. So even a top-end autorouter will spend 5 hours working on it and then get you 98% connected. And then you're really frustrated because it's that remaining 2% is impossible.
Right. Yeah. And if the machine couldn't do it, you're going to have your own set of stress trying to get those last things to connect.
Right. Well, and it turns out some of that is also that you as a person will modify your placement versus an autorouter has a harder time modifying a placement like that.
Right.
And but there's no reason that we should wait that long and be constrained so much, because on AWS I can buy multiple servers for a few minutes for less than $1 each, and just run my problem really wide across tons of servers and have them all cranking on it at the same time. And I get my results much faster, so I actually have an iterative design process, and I don't get mad at the autorouter in that case, because if it takes 5 hours,
Right.
I'm mad because I could have done the design in that time.
Yeah, of course. Right.
But if it takes 1 minute and then I tweak it, and it takes another minute and I tweak it, then it's not so bad.
Yeah, and that seems like that's more of a they've talked about like robotics and like how robots probably won't take over humans' jobs, but they will probably augment them.
Yep.
And it kind of feels like that of like the robot at the factory might not do my entire thing, but it might lift the heavy stuff that it took me, 2 other coworkers to lift something up. Now the robot and I are doing it together, and I'm making decisions on whether the, thing should stop or move or how I'm interacting with it. That kind of same idea.
Yeah, exactly. And it leaves you free to spend less of your time on reading layout constraints out of arcane PDFs and more time actually designing what is unique about the thing you're building.
Yeah, I think that's one of the other problems is everything gets downsampled to a PDF as well.
Oh god. Or like
Yeah.
even like you take a schematic PDF and you control F
Yeah.
to search for a net name, and it turns out, that PDF text box is split in 2 pieces, so it doesn't show up in the
Yeah,
search. Oh,
Yeah.
it's a nightmare.
Yeah. Well, Craig, this has been a whirlwind through, obviously different things of FPGAs and Rust and I don't even remember the other things now. Chisel,
Yep.
Scala,
Spinal HDL, everything.
Spinal. Yeah. Where can people read more about your projects and what you've been working on?
Sure. So I have a website, craigjb.com, where I try to post everything. I have a lot of stuff I need to get out there. And you can also find me on
being on the Amp Hour again is a nice motivator, it seems like.
Exactly.
There may be some recently posted things, but yeah, that's great.
Yeah, I'll get through my backlog. Thanksgiving short.
Yeah, there you go. Yeah.
And then I'm also on Twitter at Craig_JBishop. I got there a little late, so it's a little long. And then also I got to plug it. If you're in the Phoenix metro area, come out to Hardware Happy Hour every month. You can find it on Meetups, the Meetup app or Meetup website. And we meet every month, and we have a pretty good group of regulars now. So definitely come out.
Awesome. Well, Craig, thanks for being back on the show again. Really appreciate it. And hope you have a good holiday. Don't if you have too much turkey, you can always sit there, write those docs in the meantime.
Well, thank you, Chris.
All right, talk to you soon.
Bye.
Hello.
My
Can you hear me?
power went in and out for my whole house.
Oh, okay. Well, it is the winter, so I figured it was something
That's
like that. I'm glad you're not wiped off the map. I always wonder about that. Like, say an asteroid hit Arizona, I wouldn't know,
Yeah, and how
Like,
long would you
would it-
have before you find out?
Exactly. And I would just be sitting here twiddling my thumbs. I wouldn't be going, calling my loved ones or anything. I'd just be like, oh man, I wonder when Craig's going to sign back on.
And then the shockwave hits.
And then eventually I'm dead too, of course. But yeah.
Well, and then you have the last thought, wonder if his power went out.
Yeah, exactly.
Whoosh.
Yeah. Whoosh, right, exactly. That's pure movie magic there.
Right.